Hi, good evening, Pradyum. So, is this the first time you have joined this session, live session? Okay. So, you can unmute yourself and speak actually. So, which place do you belong to? Bihar. Okay. And like you are in which course? Like mechanical or what? What is your specialization? So, are you from mechanical engineering background? No. Okay. So, which background are you from? Civil. Okay. Fine. So, have you watched any of the earlier live session recordings? Okay, so any feedback for any specific feedback you have? Are you able to understand everything properly? Was the are the live sessions useful? Because today's will be the last live session for this course. So, did you find all the live session recorded videos useful? Okay, thanks. So, okay, fine. I'm actually a PhD student of IIT Bombay, and basically I am my research area is related to automotive systems, like dynamics and controls of automotive systems. So, uh, and as a part of the Prime Minister's Research Fellowship, I got this chance to conduct live sessions for this course. So till now, 7 sessions have been covered on various topics. So I have tried to make all the sessions as interesting as possible. Uh, like I also tried to include demonstrations on MATLAB and like how to solve these problems, some of these problems using MATLAB. I hope that will be helpful for although it is not included in the syllabus of this course as such, but in general using MATLAB that's a good practice, and so you can use MATLAB to solve any of these problems effectively for solving differential equations, computing inverse of matrices, and all sorts of plotting your results also. So, are you familiar with MATLAB already? So, and anyway, I think we will get started with the session. So in today's session I have planned to cover basically I have planned to solve some two problems related to multi-degree of freedom systems. So before that I just wanted to know whether you have any questions, any doubts. If not, then I will just proceed with whatever I have planned. Yeah. So I think we can just start off with the problems that I have planned to discuss. So in the meanwhile, if you have any questions or any doubts, you can stop me at any point of time and ask. Okay, what type of questions will be there in the final exam? So actually, I don't think I am the right person to answer this question. So what you can do is, I think you can post this question in the discussion forum of the course, and I think the course TAs would be in a better position to understand, be in a better position to answer your question. So sorry, actually I am not really sure about, but I think it should be similar to whatever questions that you have been solving in assignments. It will be, I think, a written exam, but apart from that I do not know much about the specifics of the type of questions that will be asked. I hope that helps. Sure. So in this week's content we have basically an introduction to multi-degree of freedom systems. So Professor Anil Kumar has solved some examples, and I think he has demonstrated how to derive natural frequency of multi-degree of freedom systems. So in this problem we will basically go through the derivation of the equations of motion of this multi-degree of freedom system. Yeah, hello Praveen. Welcome to this live session. Yeah, so we'll be considering this automobile as the system. So in this system, basically we had earlier considered the quarter car model, which was a 2 degree of freedom model, which modeled the entire car body as a single lumped mass which can just move up and down. It had just 1 degree of freedom, and also we modeled the wheels, all the 4 wheels together as a single lumped mass, and the spring and damper as the which represents the stiffness and damping of the suspension, all the 4 wheels combined together. And then we also had another lower pair of the pair, like the below connecting basically between the ground and the mass, let us say. So in that quarter car model, M1 and M2 were actually combined together, so there was only one single pair of spring and damper, like K1 and C1, let us say. So that model is the stiffness and damping of the tires. So in this model it is a one level detail, like more than what the quarter car model is. So it basically takes into account the pitching motion of the car body. So the car body can move up and down, as well as it can do some pitching motion about its center of mass. So the rotation theta, that basically represents the pitching motion, and the coordinate x3, that represents the up and down motion of the car body. Now here the spring and damper C2 and K2, they basically represent the suspension. And the masses M1 and M2, they represent the front wheels and the rear wheels. So let us say this is the front wheel. So both the two front wheels and rear wheels combine together. And this spring K1 and C1, they represent basically the stiffness and damping of the tires. So this is the general system. So any doubts in this, any questions on this? So theta basically represents the pitching motion, the coordinate x3 represents the up and down motion. So there will be, in reality, there will be more possibilities of the degrees of freedom. The car can also do yaw motion as well as rolling motion. So all those things have not been considered here, but for this particular model we will just stick to pitching motion only. So if we have to slightly simplify this system, then we can just write this system in this way. So we will just replace the car body with a single bar. Let us say it has the same mass and moment of inertia Jg, and then the rest of the system will remain the same. So there will be some spring force, let us say Fs1, Fd1, and then spring force Fs2 and Fd2. Those will be acting on the car body. So Fs1 and Fd1, so that will be for the front wheels, and Fs2 and Fd2 are the forces for the rear wheel. So this is the free body diagram, or rather I would say simplified free body diagram. And let us say we measure x3, like all x1, x2 and x3 are measured with respect to their equilibrium positions. Is that what we will assume? We will consider that they are measured about equilibrium position. So then that will eliminate the weight. Then weight does not become a dynamic force, and then we can just not consider that, we can just ignore that while writing the equations of motion. So we can actually prove that mg, the weight, will not be a dynamic force by selecting absolute coordinates and then converting them into coordinates which are basically measured relative to the equilibrium position, and then we will get the same thing. So Now if we uh, so if we just try to derive the other, like if we try to draw the free body diagrams for the masses m1 and m2 as well, and also like, so we will just repeat the, I'll just draw the free body diagram of the car body again, which will show the pitching motion as well. So we said that this force is, let us say, Fs1, and this is, let us say, Fb1, and this is, let us say, Fs2, and this is Fb2, and we are assuming that this has rotated by some angle theta. So this is the free body diagram of the car body. And so we are assuming that the anti-clockwise direction is positive, and so this is our sign convention, that anti-clockwise is positive, and so this is our sign convention. And then when we have the masses m1 and m2, so let us say m1, so this will also have the same force Fs1 acting on it, and also this force due to the damper, and let us say we have another pair of forces Fs3 and Fd3 because of the lower spring and damper, and we also have this mass m2, which will again have the spring forces Fs2 and Fd2. So these are the free body diagrams of the masses m1 and m2. So our next job is to basically write down the expressions of these forces. So before that, is there any doubt or any question? So we will just proceed with the derivation. So now, if we have these springs K2, K2, let us say M1 and M2. So the center of mass, its coordinate is given by x3 and this is given by x2. So basically this distance and these distances are given as L1 and L2. So let us write this as some distance h1 and h2. So h1 is basically L2 sin theta, and h2 is equal to L1 sin theta. And assuming theta is very small, so therefore we can write the expression for the spring force Fs1 as K2 into x3 minus L1 theta minus x2 and Fd1 is C2 x3 dot minus L1 theta dot minus x2 dot. And Fs2 is K2 x3 plus L2 theta minus x. So this should have been actually x1. And Fd2 is C2 x3 dot minus plus L2 theta dot minus x2 dot. Then the force Fs3 is basically K1 x1 and Fd3 is C1 x1 dot, and Fs4 is K1 x2 and Fd4 is C1 x2 dot. So these are the expressions for the forces, and now we can use these expressions for the forces in the equations of motion. So first let us consider the mass m1, so which has the forces Fs1, Fd1 and Fs3 and Fd3 acting on it. So the equation of motion for the mass m1, so we will apply Newton's second law. For writing the equation of motion, so it will be m1 x1 double dot is equal to fs1 fd1 fs3 minus fd3. And similarly, if we consider the mass m2, so we have fs2 fd2 and fs4 fd4. So then we can similarly write the equation of motion for m2. So it will be m2 x2 double dot is fs2 plus fd2 minus fs3 fs4 minus fd4. So we can substitute the expressions for these forces in and expand the equation of motion further. So now let us move on to for the car body, equation of motion for the car body. So it has a mass m and a mass moment of inertia jg. So they have the car body has rotated about its center of mass by theta. So let us say assume that the line of action of the spring force and damper force are the same with respect to the center of mass. So we have this force as fs1 plus fd1 combined together, and this is fs2 plus fd2 combined together, acting at the distance of L1 from the center of mass, and this force is at L2. So let us call the center of mass as G. So we will have two equations. One is basically applying Newton's second law, and the other is the moment equation. So basically Newton's second law will give us mx double dot is minus fs1 plus fd1 minus fs2 plus fd2. So that will be the Newton's second law. And if we consider moment about the center of mass G, then we will get Jg theta double dot will be sum of the moment about G. So it will be basically Fs1 plus Ft1 into L1 theta. L1 approximately it will be Fs1 plus Fd1 into L1 cos theta minus Fs2 plus Fd2 into L2 cos theta. So that will be the expression for the moment about the center of mass. So if we assume that theta is small, so assuming theta is very small, cos theta will be nearly equal to 1. So Jg theta double dot will be Fs1 plus Fd1 into L1 minus hello, welcome Deepak Dikshit to this live session. So in this session basically I am solving a problem for a multi-degree of freedom system, which is basically a car model, which is a 4 degree of freedom model, and basically I am deriving its equation of motion. So if you have any questions, you can go ahead and ask, or else we can just proceed with the problem. So you can unmute yourself and speak, or you can type your question in the chat, or whatever. If you want if you want to discuss anything specific, you can type in your query in the chat and we can discuss it later.
Yes, sir. This is for which assignment you are making?
Sorry?
Sir, this question is from which assignment?
So this question is not from any assignment. It is basically related to the multi-degree of freedom systems topic, and I have selected this problem. I am basically trying to derive the equation of motion for this car model.
Okay, sir.
So in your assignments you will also see some similar kind of problems where you have to derive the equation of motion. So this is just an example of similar kind, and this
Yes,
is
sir.
so this is basically for a car. So in this problem what is being done is, so we have this car body model. So it can do pitching motion, basically rotate about its center of mass by theta, and it can also move up and down. So it has 2 degree of freedom. So basically x3 and theta are the 2 degrees of freedom it can have. Then the springs K2 and C2, damper C2, they represent basically the suspension. The mass M1 and M2 basically represent the mass of the wheels, and
Okay, sir.
the spring K1 C1, spring and damper K1 and C1, basically they respectively they represent the stiffness and damping of the tires. So we have front wheels and rear wheels separately in this model. So what we are doing is basically representing the car body as a horizontal bar which can
Okay.
do up and down motion as well as it can rotate. And basically I am in this section I have derived the free body diagram for all the components, and applying basically for these, in this slide I have shown the forces that are acting on the system, uh, all the masses, and excuse me. Yeah. So yeah, so basically I have tried to derive the equation of motion, and here like I have shown the expressions for all the spring and damper forces, and we will basically combine all of them together in the final equation of motion. So I was basically writing the expression for the uh, I was basically writing the expression for the moment about the center of mass for the car body. So this was the expression that we get here for the moment. So we, using the values of the expressions fs1, fd1 and fs2 and fd2, we can basically get the detailed expressions for the uh, spring and damper force. So if we have to write the expanded form of the equation of motion, so we will get, so m1 x1 double dot is equal to k2 x3 minus L1 theta minus x2 plus c2 x3 dot minus L1 theta dot should be x1 actually, minus x1 and similarly for m2 we have m2 x2 double dot is equal to k2 into x3 plus L2 theta minus x2 plus c2 x3 dot minus plus L2 theta dot minus x2 dot minus k1 x2 minus c1 x2 dot. And similarly for the bigger mass, we will get the expression for the equation of motion as mx3 double dot is minus k2 into x3 minus L1 theta minus x1 minus c2 x3 dot minus L1 theta dot minus x1 dot minus k2 x3 plus L2 theta minus x2 minus c2 x3 dot minus plus L2 theta dot minus x2 dot. So this is the equation of motion for the three masses. Now we also have the moment equation, which will be jg theta double dot is equal to k2 x3 minus L1 theta minus x1 plus c2 x3 dot minus L1 theta dot minus x1 dot, this whole thing into L2 minus k2 into x3 plus L2 theta minus x2 plus c2 x3 dot plus L2 theta dot minus x2 dot, this whole thing into L. This whole thing was into L1 and this whole thing was into L2. So these are the equations of motion for the all the masses and also including the moment equation. So we have four equations. So basically four independent variables x1, x2, x3 and theta. So we have 4 degrees of freedom. So now we can represent this equation in matrix form. So if we write this equation in a matrix form, So this becomes the mass matrix, and for stiffness matrix, so this is basically the stiffness matrix. This whole thing is multiplied by the vector, state vector, so x1, x2, x3 into theta, and similarly we will get the matrix for the damping as well. So it will be x1 dot, x2 dot, some x3 dot, theta dot. So we can get the terms basically from the corresponding equations of motion, and also write the damping matrix. So we will basically get the equations of motion in a form of m x double dot plus c x dot plus k x is equal to 0. So this will be the general form of the equation of motion for this any multi-degree of freedom system. So this was how.
That
Yes.
this is the equation of motion you have written.
So this will be the general form of the equation of motion for any system. So the specific like mass matrix, stiffness matrix and damping matrix will be different for different systems. That will be the general form of the equation of motion. So here M is basically the mass matrix, damping matrix and stiffness matrix basically. Is that understood? So I have another problem here, which is another multi-degree of freedom system. So here we have the masses m1, m2 and m3 connected by springs k1, k2 and k3. So here so we again we will have to first write down the equation of motion and then derive the basically equation of motion, represent it in matrix form, then set up the eigenvalue problem. So we have to find out basically the natural frequencies and mode shapes of the system. So for that we have to first set up the eigenvalue problem for the system and then find out the eigenvalues and then basically the natural frequencies from the eigenvalues. Then we have to derive the eigenvectors from using the natural frequencies. So for corresponding to each natural frequency we will get, or corresponding to each eigenvalue we will get one natural frequency, and corresponding to one natural frequency we will get an eigenvector, and the eigenvectors together can be represented as different mode shapes. So that is how we have to basically solve this problem. So we will just start with the derivation of the equation of motion. So first we have to just draw the free body diagram. So we will have the spring force K1 X1 acting over here on, so let us say this is the free body diagram for the mass M1, and here we have K2 into X2 minus X1, and here on this mass let us say M2, we again have the same spring force K2 X2 minus X1, and here we have the spring force K3 into X3 minus X2. And for the mass M3 we have the force K3 into X3 minus X2. So that will be the only force acting on M3. So why X1 minus X2 or X2 minus X1 or X3 minus X2? Because the compression in the spring, compression or expansion in the spring will basically depend on the relative difference between these coordinates X1 and X2, X1, X2, X3. So we can just write down the equation of motion for masses m1, m2 and m3. So we have m1 x1 double dot will be equal to minus k1 x1 plus k2 x2 minus x1. Then for the mass m2, so we have m2 x2 double dot is equal to minus k2 x2 minus x1 plus k3 x3 minus x2. So our coordinate system and sign convention are like this. So these are the three equations of motion for this system. So now if we just represent this in matrix form, we will get so now if we have to write the stiffness matrix, so we will have to club together the terms corresponding to x1, x2 and x3. So first term basically which is corresponding to the x1 is basically k1, it is k2 and corresponding to x2 is minus k2 and corresponding to x3 is 0. Then in the second equation, the coefficient of x1 will be again minus k2. The coefficient of x2 will be k2 plus k3 and for x3 will be minus k3 and in the third equation the coefficient of x1 is 0 because there is no term of x1, and for x2 it is minus k3 and corresponding to x3 it is so this is basically So this is basically the equation of motion of this system. So now what we have to do is, we have been given that masses m1, m2 and m3 in terms of m, and k1, k2 and k3 in terms of k. So we have the mass matrix becomes m 0 0 0 2m 0 0 0 3m. So we have been given this clue that m1 is m, m2 is 2m, m3 is 3m, and similarly for the spring stiffness we have been given that k1 k1 is k, k2 is 2k, and k3 is 3k. So similarly the stiffness matrix will also, we can simplify that and write that, so k1 plus k2 will be k plus 2k or 3k, k2 will be minus 2k, and k2 plus k3 would be 5k minus k3, so minus k2 will be minus 2k and minus k3 will be minus 3k, and then minus 3k and 3k, x1 x2. So this will be the final equation of motion. In that similar form, x double dot.
What, sir?
Yes.
Yes, sir. I thought you were saying something. I'm listening.
So you will get, we will get the equation of motion again in this form. So now if we have to derive the natural frequencies, for that we have to first set up the eigenvalue problem. So let us say if we have a solution of the form, say x naught e to the power lambda t, and if we substitute that in the equation of motion, we will get so this will be the equation of motion, if we substitute it in the equation of motion, so basically we can write lambda square into m plus k into x naught. So since e to the power lambda t is not 0 for any real value of time t, so then we have the, the equation in this form. So then x naught is basically the let us say amplitude of the displacement, like the state vector, and then so for this equation to have a non-trivial solution, we will have determinant of lambda square m plus k will be 0. So basically this is the characteristic equation. Or basically the eigenvalue problem. Here, so if we say that so let us say lambda square is so let us say lambda is, if we substitute lambda is I omega, then omega will be the natural frequency. So so we can solve the characteristic equation either for lambda or omega, whatever is convenient. Finally, omega is basically the natural frequency that we are looking for. So if we write the determinant for this problem, it will be So basically this is the determinant that we have to calculate. So basically the roots of the characteristic equation will be lambda and which is basically I omega, and from basically using the roots of the characteristic equation, and so for by solving the equation for, so it will be here, it will be a sixth degree polynomial in terms of lambda, or if we substitute lambda square by some variable, let us say some beta or something, then it will be a cubic polynomial in terms of cubic equation in terms of beta. So we can basically find out the roots of this characteristic equation and get the eigenvalues. Basically lambda square, and then we can use the eigenvalues to determine the eigenvectors. So basically if we have the three eigenvalues, basically lambda 1 square, lambda 2 square and lambda 3 square, so then we will have basically lambda 1 square m plus k into x1, or let us call it as capital X1 is equal to 0 vector, and similarly we have lambda 2 square into n plus k into capital X2 . So we will have these three sets of equations, so basically x1, x2 and x3 are basically eigenvectors corresponding to lambda 1 square, lambda 2 square and lambda 3 square. So these are the eigenvalues. So basically if we solve for x1, x2 and x3 using these equations, we will get the values of the eigenvectors x1, x2 and x3. and so x1 will be some vector, so say a1, b1, c1, x2 is basically a2, b2, c2, and x3 is, let's say, a3, b3, c3. So these are the eigenvalues, and then or basically the mode shapes. So we can represent each eigenvector as mode shapes. So we can just write like a1, b1, c1, whatever. And so we can basically plot the mode shapes in this way. So similarly for, so let us say it can be ai, bi, or ci, I equal to 1, 2, 3, whatever. And this is how we can basically plot the mode shapes. So so in this problem basically we have seen the approach of how to get the natural frequencies and mode shapes. So first we started off with drawing the free body diagrams for each of the system masses m1, m2 and m3. Then we applied Newton's second law to each of these masses and derived the equations of motion. Then we represented the equations of motion in matrix form, and we basically found out the mass matrix and stiffness matrix, and also we basically find out the mass matrix and stiffness matrix for this particular problem. And then we saw the approach of how to set up the eigenvalue problem in terms of lambda square. So and basically we get how to get the characteristic equation is basically determinant of the matrix lambda square m plus k. So if we solve for, so we will basically get a cubic equation in terms of lambda square, or basically 6-degree equation in terms of lambda, and using the roots of this characteristic equation we can get the eigenvalues and hence the natural frequencies, let's say omega 1, omega 2. So let us say they are the natural frequencies. So omega 1, omega 2, omega 3 we basically get using lambda is equal to I omega, and then we get the eigenvectors x1, x2 and x3 of the form ai, bi, ci, of that form, and then we can just plot the mode shapes as the way it is shown. So that's all from my side for this week's live session. So I hope all the live sessions were useful, and this was the last session basically for the 8th week of this course. So I hope all of you found these live sessions useful, and so there is a feedback form that has been floated in the for the course, or basically, and also for each week's live session. So I request all of you to fill up this feedback form and let me know how you found the live sessions. What all do you think went well, and what do you think did all the live sessions meet your expectations, and what went well and what do you think needs to be improved. So please give me all the feedback. So thank you very much, and wish you all the best for the final exams. Thank you.